it almost maybe will be a little like silly, but so random definition here that is just very generic. If f is a continuous and differentiable function on the open interval from a to b, so here I just have an image of something that's continuous and differentiable from a to b, then there exists a number c in that interval a to b such that the slope of c is essentially equal to the average rate of change between a and b. So if I kind of connect A and B, I can see that average rate of change. As long as my function is continuous and differentiable on that entire interval in between, then there has to exist some point C that has that same instantaneous average rate of change. So essentially the visual is just you would kind of think about sliding that average rate of change segment until it becomes a point of tangency, which may be right there. Obviously, the average rate of change means average. So along my curve, sometimes the slope is less than that, sometimes it's more than that, but on average it will be exactly that. At some point, because we're continuous and differentiable, our slope is really negative, and then it flattens out, and then it's going to gradually become more positive at one moment, actually having the exact same value as that average rate of change. So I think logically makes sense. You'll be asked to do some of these following with it on your homework. So consider the graph of, this is a quadratic. Find the equation of the secant line joining negative 2, 4 and 2, 0. Go ahead and do that on your own. Write the equation of this secant line. Zach, what'd you get?
Y equals negative x plus 2.
Anybody get anything different? Good. So there's our slope of our there's our secant line. Very good. Use the mean value theorem to find what point on this interval from negative 2 to 2 such that the tangent line at x equals c is parallel to the secant line. So we're essentially find the location that has a slope of what, Ellie? -1. Very good. So find the location on this that has a slope of -1. We're essentially going to take the derivative, set it equal to -1. So the derivative is negative 2x minus 1. And we want to find out when this equals -1. So if we add 1 to both sides, negative 2x equals 0, it's at x equals 0. That's the x coordinate. So it's right here. The y coordinate is, just plug 0 back in, 6. Now, just because it popped in my mind right now, the mean value theorem says there has to be at least one location, but it obviously could happen multiple times. If you had like a polynomial that fluctuated a couple times in between, would be the easiest way to see that. But that's part B, and then write an equation of this tangent line. So go ahead and do that on your own. And Haley, what'd you get? Good. Good. So I just graphed all three of them for you. So if I could just look at -2 to 2, but I did the -10 to 10 window. You've got your secant line, you've got your, you can kind of see obviously where that happens. Any questions? Simple enough. All right, so determining whether or not the mean value theorem can be applied on the interval, if it can, find all the values of C in that interval such that this mean value theorem applies, where the instantaneous rate of change at some C point equals the average rate of change. So the determining whether or not the mean value theorem applies, it has to be continuous and differentiable on the entire interval. So we first need to check on this first function, which I don't really love the format of that. It's just easier to distribute your x and turn it into a polynomial function. Is that differentiable on the entire interval from -1 to 1? Yes, it's just a cubic polynomial, so we don't have any kind of tricky things to worry about. No asymptotes, no holes, no sharp corner points. So we're good with the differentiable and continuous. So that's all set. Now we just need to find the average rate of change on that interval, and then we'll then find the location. So go ahead and find the average rate of change of this function from -1 to 1. Connor, what do we need to do first before we can jump right into that?
We need to find the values for 1 and -1.
Right, we need to find the point. So -1 and 1 are going to be the endpoints of our interval. We have to find out what those are so that we can find the slope between them. And Michelle, what did you get for the slope between the 2 points? Okay, let's back up. What did you get for the coordinates for the -1?
2.
You got -1, 2?
Yeah.
Did anybody get anything different? Okay, so we got to back up, basic plugging in. Michelle, what's -1 cubed? -1 minus what's -1 squared? But it's minus that, right? Is that where your mistake was? So these little small steps are, obviously the culprit of the larger picture here. You should have gotten what, Michelle? 0. Good. When you plugged in 1, what did you get?
-2.
Right, and that one's more accurate because we didn't have that -1 floating around. So when you find the slope between those 2 points, Stephanie, what'd you get? The slope of the secant line between those 2 points. Very good. Okay. So now that's our average rate of change. We want to find the moment where our instantaneous rate of change is that. So take the derivative and set it equal to that average rate of change. So 3x squared minus 2x minus 2 equals that -1 average rate of change. And then solve. It's a quadratic, so add your 1 over. Oh, is it factorable? 3x and x. 1 and 1. Minus and plus. Very good. So we get x equals negative 1/3. Is that in our interval? Yes. And x equals 1. Is that in our interval? Okay. Quick note on x equals 1. It is at the end point, though. And if you look at the mean value theorem definition, it says there exists a number c in the open interval. Yes? So something between the endpoints, but not including the endpoints. Yes? So when we... And it would be kind of weird because if I graph this, your tangent line would be at the end of your interval, minus x squared minus 2x. If I look at this from negative 1 to 1, and I did this exclusively from negative 1 to 1, here's my average rate of change. Here's the negative 1/3 point that we got. The other place that has a slope at that exact moment is right there, but it's on the end point, so we're not going to include that one. Are we clear with that? So include the C that's between the endpoints, not one that's actually at an endpoint. And then find all values for C. It's not even asking for the point there, so your C value is just the negative 1/3. Any questions on that? Number 2, a little bit trickier because it's trig. Again, go ahead on your own, find the slope of the secant line, and then try to find the C values on your own. Was there no done? Okay, good. Raise your hand if you're done. Raise your hand if you're stuck. Jalen, where are you stuck at?
Well, I'm pretty sure it's all wrong, but I have 2 cos x plus 2 cos of 2x. And I don't know 2.
Equals what?
0.
0. Raise your hand if you have that. 2 cosine x plus 2 cosine 2x equals 0. Loud and proud. So I'm guessing some of you don't have that. That is correct. Raise your hand if you know what to do with that.
I tried to factor, but I didn't know how to take out a cosine of the
Yeah, you can't because they're different, right? So let's back up here. The 2 points were 0, 0, and pi 0. Any questions on that? That's just knowing your values and plugging in appropriately. So your slope is 0 between those 2 points. So your average rate of change is just 0. So when we take our derivative, we're going to set it equal to 0. So the derivative of 2 sine x is 2 cosine x. The derivative of sine 2x, again, just knowing your derivative shortcuts and making sure you do your chain rule here, because the derivative of sine 2x is cosine 2x times the derivative of what's inside. So this is where Jalen was stuck. She wanted to factor, which I think is everyone's first instinct, but then you immediately realize that cosines of x are not both cosines of x. So you can't just factor something out in front. I think based on the markings on my paper, there might be a little hint there. What? It's a double angle, cosine of 2x. So I just replace that. Cosine of 2x is 2 cosine squared. Cosine of 2x is the one that has like 3 options. Yes? I'd show there's one that has just a sine squared, there's one that has just a cosine squared, and then there's one that's got a little mixture of sines and cosines. Because this first part was already cosine, I replaced it with a cosine squared version, distributed my 2, and now it's factorable. So I rearranged it, divided out the 2, and factored it. So I'll give you a second to catch up to speed there. And make sure, and I just, in general, you just have to get used to when you get not necessarily stuck, but make sure those cosines of 2x or the sines of 2x are kind of setting off an alarm in your head that I know I can do something with that. Obviously, the more times you run into them out of context, the better that will get. You'll naturally start thinking of that. So once I factor it down at the bottom, I have the 2 cosine x minus 1 factor and the cosine x plus 1 factor. So either the cosine of x equals a half or the cosine of x equals negative 1. So go ahead from there and find your C values. Adam, are you done? Oh. Okay. Your posture was telling me otherwise.
Oh.
Okay. Adam, what do you think?
Cosine x could equal 60.
Okay, what's the pi over 3? Yeah. So x could equal pi over 3.
Or x could equal 180.
Pi.
Yeah, pi.
Okay. Thoughts, comments on that? Jalen?
I
Okay. Comments on that, Liam?
Can't equal pi because that's one of the endpoints.
Okay, so even though pi is the solution for that, it's one of the endpoints of your interval. Okay, so we're going to ditch that one. Anything else? Steven? Right. 5 pi over 3 is just out of the interval. So yeah, the slope will equal 0 there, but it's not in the mean value theorem interval that we're looking at. So the answer is just pi over 3. Okie doke? Last one. When an object is removed from a furnace and placed in an environment with a constant temperature of 90, its core temperature is 1500 degrees. 5 hours later, the core temp is 390 degrees. So 0 hours after it's been taken out, it's 1500 degrees. You're going to extract kind of points from the word problem. 5 hours after it's been taken out, its temperature is 390 degrees. Why must there exist a time in this interval when the temperature is decreasing at a rate of 222? So essentially, as you know, when you first take something out of a hot whatever, it's going to decrease at its fastest rate. And then it's going to always be decreasing towards that room temperature, but it's going to become less and less severe as it's been out for a while. Yes? That's kind of the Newton's law of cooling that you looked at a little bit last year. So the average rate of change between 0 and 5 hours is, oh boy, let's fight the calculator. 1500 minus 400 would be 1100. 1110
Negative.
over negative 5. Oh, I did mine maybe in the opposite order.
And yeah.
So, I should do mental math here, but I really just don't want to think, and I want to do long division. How many times is 5 going to 1110?
222.
Perfect. So, obviously, your average rate of change is negative 222. So you would just say, based on the mean value theorem, since the average rate of change along this interval is negative 222, there must exist some moment in time between the hours of 0 and 5 where the exact rate of decrease is 222. It's just an application. Okay? So your homework's at the bottom, 224, 31 to 57. You're going to have a quiz on Friday. It's pretty short, but there's a small review packet for that, right? There's a small section of just multiple choice questions. So there are only 9 or 11 of them, but start taking a look at that because you can now, with the mean value theorem, do the first probably 6 or 7 on there. So this is not a very long assignment or a very difficult one, so I think, tonight might be a good time to look at that. So if you have questions tomorrow or Thursday, because we're not doing a separate review day.
I'll be here early tomorrow.
Okay. On that, so start looking at that, and I'll take questions on that as we have them.